Okay, let's now move to the second part of this lecture, the probability fundamentals. Right, so we're at the section 1.2, so I highly encourage you to reread the textbook. This section is going to talk a lot about the very basics of the probabilities. Sometimes that look too trivial, and it's sometimes it's not clear why they are even here in a graduate probability class, right? So we are going to talk about the assumptions or probability. Right. So here the main purpose is really to make the entire probability statement to be more rigorous, right? So when you took the first undergraduate class in probability, a lot of times you sort of like mix the intuition of some certain probability statement with the probability analysis, right? So here the real purpose is really to encapsulate the most important concepts and axioms, and so that in the futures when you want to derive some non-trivial mathematical statement about certain probability phenomena, it becomes a rigid and pure mathematical analysis of manipulating the symbols, instead of often that you need to go back and forth and check whether the intuition is matching with the statement. Right, so the discussion so far has been quite vague. So I think it would be best to illustrate a number of examples, right? So when we talk about probability, we usually use the probability in very different ways, right? For instance, you can talk about like the first example. Let's say that we can talk about toss a coin, and when you toss a coin, you usually make a statement looks like that. Probability when you toss a coin, the coin turns out to be a head, right? So it's a half, right? So this is one type of the probability statement we usually want to make, right? And there are also other types of probability statement. For instance, so let's say that I'm going usually when you in the weather forecast, you are going to see that people say that the probability it is going to rain, going to rain, it's say that 70%, right? So I'm making up this number, right? So this would be the second type of probability statement we are going to see, right? So and the third one would be it's again like sometimes you also see that when in the medical science they try to do a lot of their assertions like like the chance assertions say that if you smoke, right, the probability you're going to develop cancer it's going to be say like 10%, right? So when you say the probability, sometimes it's not really probability, it's really just called as chance, right? Right. So when you examine all these three types of assertions carefully, you clearly see that they are not really referring to the same thing, right? So in the first one, basically you toast something, you just look at the outcome, right? And it's intuitively clear that like after you toast something or you sample a random number from the random number generator, you see something, and either the certain statement is true or false, right? So you can intuitively define the probability in a quantitative way, right? So, but now when you talk about probability of weather, like, is it going to be like who is tossing a coin, right? So you sort of like we really cannot really use this kind of coin tossing paradigm to talk about the weather, right? So is it the god is tossing a coin, like the coin is head and it's raining, otherwise it's not raining, right? So the whole statement start to feel a bit strange, right? So again, like this probability is also right. It's also similarly equally applicable here, right? So imagine you are an individual, right? When you smoke, right? There's only one chance you either get a cancer or you don't get a cancer, right? Right? Either you get that or you don't get it, right? So what is the probability? What do we mean when we talk about the probability, right? So when you look at all these statements, so my major point is that a lot of time when you were in undergraduate, right? So people really get confused or really don't deliberately like distinguish all these three concepts: probability and belief and also the chance, right? So right, so the second one, right? So the second statement and the third statement, it's more about the belief. It's not really about the probability, right? So when you think all these statements, three statements in your mind, then you start reading the section 1.2, then I think one of the very important exercises really just that when you read all the definitions and the lemmas, can you relate back all these three assertions related to probability and sort of start to feel the subtle difference, and also feel that why do we need an extra layer of abstractions of the axioms and lemmas to really abstract out the subtle difference between all these three concepts. Okay, right? So in other words, let me just repeat, right? So you just look at your section 1.2 and also think all these three assertions, just internalize all these three assertions and try to grab the very subtle difference when we talk about these when we talk about these three statements. Even all these statements are related to the probability statement. Okay, so let's move to a bit of the dry part, the definition, right? So, when we talk about any probability statement, there's always a probability space, right? And this probability space, when we talk about space, it really consists of three elements: 1, 2, 3, right? There are three components that's associated with this probability space. The first one was what people call the sample space, right? So usually people use omega to denote the sample space, right? This is basically the set of all possible outcomes, right? So let me just finish out the entire definition and give you an example, right? So this is the sample space, and then after the sample space, we are going to talk about the event. Event basically is called, when we write that rigorously, it's called a family of sets F, such that for any F inside the F is a subset of, of the probability space. Right. So basically, like let me just even finish the third one. And the third one would be a probability function that's mapping the event set to the real number, so to the 0, 1, right? So, and additionally, we need certain extra properties in order to make sure that this is a probability function, right? So this is the definition 1.1 in the textbook. Right? So you can also read your textbook while watching this lecture video. So what does that mean? Like the structure here, I think, like if you just did one probability cast, the structure here look very strange, right? So sample space, like, so let's call that we use a roll of dice as an example, right? So the dice basically can have 6 possible outcomes, right? So basically it could be one of the numbers that's between 1 to 6, right? So now when we roll a dice, the probability space basically is really just 1, 2, 3, 4, 5, 6, right? So that corresponds to all these 4, 5, 6 possible outcomes, right? So this is the probability space. And then we can talk about event. Event, basically one event is basically so mathematically it's a subset of the probability space, right? So say that when we can define the event to be 1, 2, right? So now we say that the probability of this event, let's call this is E1. E1 happens when we say this kind of things is really just that probability of the outcome falls into this event, falls into this subset, right? So let me just repeat, right? So when we have been talking about events, right? So when events is a very, very good example of highlighting that when you revisit your probability knowledge, and all of a sudden you realize event would before this class probably you just interpret event as literally some event happens, right? So but when we talk about the mathematical definition, the events are really just considered as a subset of the outcome, right? And when we say an event happens, it's really just that the outcome falls into this subset, right? So the outcomes, right? So has 1, 2, 3, 4, 5, 6, right? So this would be the probability space of the rolling dice example. And event is defined as, right, so when we, so this the circle I'm highlighting here by the pink lines, right? So this would and this would be an example of event, right? So again, the event equal to subset, subset equal to event, right? So this is conceptually, I think when I was taking the probability class, this is the first non-trivial concepts I feel I encounter, right? I thought all of a sudden I start to feel that the way we make things rigorous is very different from the intuition you have. Right, so this is one event, right? So and probability this event happens is basically the probability the outcome of the dice, right, is from 1, 2, or 4, like in this particular example, right? So this is the probability, right? So now when we talk about the probability, it's actually connects to the third component, right? So we want a probability statement here, right? So the probability statement, the probability function, right? The probability here, it's actually a function, right? And this function has this property that at least for any event that's basically for any subset of omega, right? We need to be able to map this event to a number, right? So this function needs to be well defined on whatever places that you think you should be able to define, right? So let me just repeat. Like I have a set of outcomes, then I can talk about a set of all possible set of events, right? So in this discrete settings, if I have only 6 elements, right, the total number of subsets, total number of subsets is what? It's 2 to the 6, right? So we want to make sure the probability function is able to map any event to a real number, right? So so basically it just says that for whenever I'm able to properly define an event, the probability function should be able to map this event to a number that indicates the probability this event happens, right? So the probability function itself is part of the definition. And of course, right? So in order to make this probability function a legitimate function, then we also need to impose additional constraints, right? So the additional constraints we are seeing here is the definition of 1.2, right? So a probability function is that maps the P to the F, right? The set of all events, right, to real number, and then that has to satisfy a number of conditions, right? The first condition is for any event, event E, it's written E in the textbook, belong to F, right? So this is an event. This is the set of event. Event itself, it's a subset of omega, right? So I have been repeating this multiple times. For any events that's within F, we need the probability function to have this property. It's all the probability we are talking about should be between 0 and 1, right? This is the first property we want. And the second property is that know that omega itself is a subset of omega, right? So omega on its own can also be considered as an event, right? The event is really just that the probability one of the 1, 2, 3, 4, 5, 6 it's going to happen, right? So and obviously we do want the probability of omega to be 1, right? So if I look at the entire probability space, the probability the outcome falls into this space has to be 1, right? There shouldn't be any elements that's outside that space that you observe. Otherwise, it contradicts to the definition of the probability space, right? The third one would be the mutually exclusive rule, right? So mutually exclusive rule, right? Exclusive. So basically the intuition is pretty simple, right? So let's say that this is the probability space omega, right? So I can talk about two events, right? So two events, each event is a subset, right? So let's call this is E1, this is called E2, right? So when E1 and E2 are subsets, we can talk about the intersection of the events, and then we can talk about the union of the events, right? So those are really just the set operations. I'm saying out things in a different way from what I'm writing. So this is the interaction of the event. So I'm not so the, and then this is this is the this is the union of the event, right? So the third probability properties basically says that in case the interaction of two events is empty, then when I say that the probability one of this event happens, right? One of this event happens, one of event 1 or event 2 happens, is going to be sum of event 1 plus sum of event 2. Right. So this is quite intuitive, right? So when let's really just go back to the dice statement we have been talking about. We have 6 elements, 1, 2, 3, 4, 5, 6, right? So let's say like the first event, let's call the event 1 to be this is our event 1, right? Event 1 basically means that the outcome is 1 of 1, 2, and 5, right? So and let's also call that the rest of them as the second event, right? So this is the E2, right? The outcome of let me just erase that part, not include that to make the example a bit more non-trivial, right? So let me just define the green event as the outcome of 3 and 6, right? So the third statement, the mutually exclusive principle, basically said, what if I compute the probability of either event 1 or event 2 happens, right? So this is the either, so in English, this is either event 1 or event 2 happens, right? So this should be not surprising. This should be either probability event 1 plus probability event 2, right? Right, so you can even verify that on the fly, right? So so the probability event 1 happens, right? So the probability that event 1 happens basically is the 3 divided by 6. 3 basically means that there are 3 elements here, right? So this is the event 1, and the probability of event 2 is going to be 2 divided by 6. For the same reason for the event 2, there are 2 balls here, right? So I'm assuming the dice is a uniform dice, right? So then probability either event 1 or event 2 happens. Basically in English, this means that probability 1 of 1, 2, 3, 5, 6 happens. 1, 2, 3, 5, 6 happen, right? It's really just that 5 over 6. Basically, if you sum up this 2, you get 5 over 6, right? So it's very obvious that this should be the property that's needed for the probability function, right? So if any probability function that satisfies all any probability function that satisfies all these 3 conditions, and we call that a legitimate probability function, right? So so here, like, there's also one more subtlety here, right? So for most part of this course, we assume this probability space is a discrete space, right? So when we talk about discrete space, especially it's finite, then we can talk about all possible subset, right? All possible subset, right? And but then like you should really just be aware that when the probability space is a continuous one, right? So the way we define the f is going to be much more subtle, right? Right. So we sort of now this really just links to the real analysis, right? Maybe some of you are not aware of that, but in case you're not aware of that, you can safely ignore what I'm saying, right? So when omega is a continuous space, say that it can be any value between 0 and 1, then f needs to be so-called the Borel set. Right? So, and there's also a notion of measurable notion here, right? So for instance, if you define f to be the set of all irrational numbers, numbers, right? So there's a question on the what's the probability that x belongs to let me say let me call an event E, not F, right? Sorry, an event to be the set of all irrational number, right? So this is clearly a subset of the probability space. Then when we want to talk about what's the probability S falls into E set when X is sampled uniformly from 0 and 1, right? So something something strange is happening, right? So basically we are asking that if we sample uniformly we produce a uniform sample from 0 1 from the 0 1 support, what's the probability the number you sampled is an irrational number, right? So that basically it's really giving you an example that when things become continuous, right? So you start to need to answer this kind of strange questions that's sort of related to the measure theory, right? So if in case you need to make the whole argument more rigorous, you want to understand how the more rigorous definition can be done for the continuous space, then you do need to consult a standard graduate probability textbook from the math department, right? So, but again, as I've emphasized that so far, like for the purpose of discussion, here we just need to focus on the probability space being a discrete one, right? So now this is the definition 2 and definition 3, right? So we can also like use the definition and look back to the polynomial verification problem, right? Our polynomial verification problem is that we are given two polynomials. We have a randomized algorithm, and sometimes the algorithm gives you a correct answer, and sometimes it gives you an incorrect answer, right, with pretty low probability. So now we can talk about the probability space and events and etc. for this very specific example, right? The probability space basically is the set of numbers 1, 2, 3 up to 100D, right? So basically, if you recall what we have been doing very further up, right? So we were talking about like trying to sample a number that's between 1 to 100D and test whether f of this number is the same of g of this number, right? So when we sample a number, right? So this is really just the probability space we are talking about, right? So this is the so I'm heading towards trying to give you a concrete example of like when you have a stochastic process, what are the events and what are the probability space. This is the probability space, right? And then we can also define sometimes called something called a bad event, right? That would be really all the numbers, right? For all the numbers that's inside omega such that, right? So fx equal to gx, right? So we are sort of need to make the assumption that we are sort of under the assumption that f doesn't equal to g, right? So otherwise our testing is a trivial testing, right? So the more difficult part has been on the case where f doesn't equal to g, right? So we can talk about bad event. Bad event means that despite that f doesn't equal to g, somehow this x passes our test, right? So this would be the definition of bad event, right? So definitely, right, bad event would really just be subset of numbers, right? So I'm just drawing some arbitrary things up, right? So a subset of numbers that's out of this entire omega set. And what we have been arguing is that the probability of this bad event, right, let's call this EB, right? So the probability of this EB is going to be less than or equal to 100D divided by D divided by 100D. This is 1%, right? So you sort of can see, right? So we have been defining quite a number of important concepts, right? So one is the probability space. And with the probability space, the probability function is also pretty straightforward, right? Probability function, this function itself really is just the uniform function, right? Uniform function, basically, if probability, the outcome is I, is going to be 100, well, d 1 over 100, right? So I belongs to 1 to 100d, right? So this is the probability function we want to define, right? So as I mentioned, we need to be able to define all three items in order to well define our probability process, right? So the set of events and the probability functions, and as well as the probability space over here, right? So now, so let's just record that what we have been doing so far, right? So we come up with a rigorous way to define the probability space as well as the probability function. We can even articulate what we mean by bad event for the algorithm we described just now, and give a bound on the bad event, right? So again, as I mentioned, the high level idea of this conceptual definitions is really just to make sure that starting from today, when you look at the probability processes, you are able to make rigorous. Okay, then next, after we finish the definition, let us move to the lemmas, right? So another thing we need to pay a lot of attention to in this kind of theoretical courses or theoretical research is that we do need to separate very well between the definition and the analysis, or the lemmas, or theorems or propositions, right? So what we have been talking about is really just the definition of probability space and the probability function, right? So for the two definitions we mentioned above, you should just assume they are given for granted, and those are really the only thing we are assuming. And then we want to be able to derive a collection of lemmas theorems that help us to simplify our analysis from time to time, right? So basically, you can imagine that we are trying to build up a collection of tools based on the definitions, and then we are going to reuse the tools again and again, right? So that means that the next two lemmas we are going to show are going to be pretty elementary, but we just want to be able to highlight that all these lemmas can be derived from the very small set of definitions we described just now, right? The first lemma would be for for any for any two events E1 and E2, we have probability of E1 union E2 equal to probability of E1 plus probability of E2 and minus probability of E1 intersect E2, right? So intuitively, it's really very clear, right? So it's really just the kind of set principles we are using, right? So when you did the when you look at the set theory, very elementary set theory in some of the math courses you took, we sort of know that E1, if we want to count the number of elements, we do have this result. E1, all the elements, if I count all the elements of the union of E1 plus union of E1 and E2 equals to E1 plus E2 minus E1 intercept of E2, right? So basically, it's really just that if I want to count the whole area, what I need to do is to first count the left hand side and then count the right hand side, and then we are sort of doing overcounting this component twice, right? So we sort of minus this component here, right? So this is really the things you are already familiar with, right? So based on this, basically the whole thing here is pretty intuitive, right? So we are really just doing this so we are really just doing that this counting independently and subtract the overcounting part, right? But what's really needed, right? So in the analysis, or if you look at the proof of the textbook, right? So we don't directly go from this intuition. What we do is really to leverage the definitions we have been described, and just use those kind of definition to prove this statement, right? So let's walk through what's inside the textbook, right? The textbook first says that let me compute the probability of E1, right? So probability of E1 equal to probability of E1 minus E1 intercept of E2 plus probability E1 intercept of E2. Why is that? So again, let me just draw the Venn diagram we have just now, right? So let's assume that this part is E1, right? So now I can sort of decompose this E1 into two components, right? The first component is this little part. This little part corresponds to the component, the formula right here. It's really just the E1, E1 minus E1 intercept E2, right? E1 intercept of E2 is really just the part over here, right? So this is the E1 intercept of E2, right? If I use the whole E1 minus this part, right, I'm going to get this black part out, right? So let me just draw this black part again, right? So this black part, right? So this is the first component here, right? The second component, as I said, there is really just the intersect term, right? So this is this part, right? So this is this part, and this is this part, right? And our observation is that if I look at these two events, right? So if I look at the black area and the green area, they are mutually exclusive. Mutually exclusive, right? That means that again, like we have the statement that if E1, E2 mutually exclusive, right, which means that E1 intercept with E2, it's empty, right? So let me not even write E1, E2, right? Let me, because I have been using E1, E2 here, right? So let me say E and E prime are mutually exclusive, which means that E intercept of E prime, it's empty set. Then probability of E1 E union of E prime equal to the sum of E plus probability of E and E prime, right? So basically I use E to be this black one and E prime to be this green one. So that's the reason that there are two mutually exclusive events. If I express this E1 into these two events, it's really just the summation of these two, right? So this is the first part. Let me just write that cleaning. Write that down again so that our notes are a bit more clean. E1 minus E1 intercept or E2 plus probability of E1 intercept of E2, right? This is the first statement. And the second statement, we can use the same principle and get this one. Probability of E1 minus E2 minus E1 intercept E2 plus probability of E1 intercept of E2, right? Right. So far this thing is clear, right? So now we want to be able to use this tool to get our lemmas out.